Thanks.
Thank you very much, and thank you to the organizers for inviting me to speak today. It's certainly a great pleasure to finally be back in person and to be speaking to an audience instead of my computer screen alone in my office. So today I want to talk to you about some work that we've been doing in my group on combining low field NMR instrumentation and parahydrogen hyperpolarization. So when I'm talking about low field NMR instrumentation, really what we're thinking about is compact NMR devices. So moving away from our very large lab-based superconducting magnets to, for example, solid state magnets or electromagnets that are more portable and more affordable. But of course, if you do this, you need to sacrifice magnetic field. And with that comes a loss of resolution and also sensitivity. So the sensitivity problem that we have is that, of course, our signal in NMR comes from this very small population difference between the two nuclear spin levels. And for a proton, this is only 3.5 parts per million per Tesla. So this is a particularly acute problem if you're working at low magnetic fields. So the way we can overcome this is to use hyperpolarization. And so the basic idea of hyperpolarization is just to take your system out of equilibrium, overpopulate one of the energy levels, and so increase the polarization and therefore your signal. And since we're starting from such a low baseline, there's huge opportunities here to boost our sensitivity by many orders of magnitude. Now, if we're going to do this and combine our hyperpolarization with compact NMR instrumentation, we really need to focus on methods that in and of themselves are relatively compact and inexpensive. And it's for this reason that I'm particularly interested in parahydrogen hyperpolarization methods. Now, in this talk, I don't want to tell you so much about how we use parahydrogen hyperpolarization to enable applications of compact NMR, but rather how we've been developing some low field NMR instrumentation to look at the parahydrogen hyperpolarization and understand it a little bit better. So just for those who are not familiar with parahydrogen, just a reminder of what it is. So we've got molecular hydrogen, H2, which of course is 2 protons, both spin half. But because of the overall symmetry, we need to combine these into either a triplet state with total spin 1, and that's orthohydrogen, or the singlet state, which is spin 0, and parahydrogen is a singlet state, so it's only 1 energy level. And so in a sense, this is a pure nuclear spin state, so it's kind of like it's purely polarized. Now, because of coupling to rotational states, we have a regionally large energy gap between the singlet and the triplet state, and the transitions between these are symmetry forbidden. So if we enrich our hydrogen gas in the para state, then we're essentially locking that in, and we can store the parahydrogen to use it when we need it. Now, here we have, if we have enriched our hydrogen gas in the para state, we have essentially a bunch of protons in pure nuclear spin states, but we're not really any further ahead because we have no signal because this is a singlet state. So what we need to do is we need to use this parahydrogen in a chemical reaction in order to break the symmetry of the 2 protons and enable hyperpolarization. So there are a number of ways that we can do that, and some of the later talks in this session will talk about, for example, hydrogenative methods, but I'm going to focus here on the signal amplification by reversible exchange, or SABR method. Now, SABR is based on basically a catalytic method for transferring polarization from parahydrogen to a target molecule, our target substrate. And so this cartoon kind of shows how we do this. So we start off with a metal center, so our catalyst in solution, along with our substrate. So that's the thing we want to hyperpolarize. We add parahydrogen as a gas, and then we shake our NMR tube for the parahydrogen to go into solution. So now our parahydrogen can reversibly bind to our metal center. That breaks its symmetry, so they become these 2 protons are hyperpolarized. And our metal center, crucially, is also binding 1 or more molecules of our substrate. And if we carry out this reaction in a very weak magnetic field, a specific field, for example, 6.5 millitesla, then we get spontaneous transfer polarization across the J coupling of our catalyst into our substrate. And then when we have an exchange event, we exchange our hyperpolarized substrate into solution, and we refresh the hyperpolarization on the hydrides. So this becomes a sort of catalytic process that as we shake our NMR tube, we supply more parahydrogen, we have more exchange, and we build up polarization on the substrate in solution, then we put the sample into the magnet and detect our hyperpolarization. And we can get very high levels of enhancement on the order of thousands. So just to show you a little bit how this looks in real life. So this is a former PhD student of mine, Olga Semenova, in real time. So you come into the lab, you see lots of people shaking NMR tubes, which is quite funny, but it's effective. And you can see how pleased she is at the end of a few seconds to get a nice signal enhancement on her sample. So this illustrates that actually running this experiment is quite simple, although what's happening under the hood can be quite complex. But what you also notice is that it's a two-step process. The actual polarization is happening in an ultra-low magnetic field, in the fringe field of the magnet, and then we're detecting at high field. And so that means that what's happening in the actual SABRE experiment is a bit of a black box, and we have to move the sample through a range of fields at an indeterminate time into our spectrometer for detection. So the goal of this project was to ask whether we can actually do in situ SABRE in the ultra low field, where we both polarize and detect in the same place without having to move our sample, where we can just cycle between the fields. And to do this, we're doing actually Earth's field NMR detection with in situ SABRE. So that may seem a bit of an odd choice, as the Earth's field is so weak, 50 microtesla. But there are a number of reasons why this is useful. So first of all, polarization transfer for SABRE occurs in a range of fields from 0 up to around 10 millitesla, where transfer to non-proton nuclei is near 0, and transfer to protons is in the millitesla range. And so we want to access all of those fields. And so we need to do something about the Earth's field because it's always there. And so in these experiments, we're choosing to work with the Earth's magnetic field, use it for detection, and also do active cancellation to access evolution in lower magnetic fields. The other benefits of this is we can just commercially buy really cheap instrumentation to do Earth's field NMR, and the Earth's field NMR probes that you can buy already have an electromagnet that work in millitesla regime, so can provide that 6.5 millitesla for standard SABRE transfer. So this is what our system looks like. We've got our Earth's field NMR probe that has a B1 coil for the RF, some simple first order gradients for some basic shimming, and then the electromagnet to provide that millitesla field. And inside we put a very simple reaction cell where we can bubble parahydrogen through our sample, and we're just controlling that with a series of valves, and we're constantly flowing the parahydrogen through this system. So this is just a very simple pulse sequence to explain how these experiments work. And so in order to go from doing the normal Earth's field NMR experiment to doing SABRE, all we have to do is add in the bubbling of parahydrogen. So what we do is we start bubbling parahydrogen, then we switch on this electromagnet to the field that we want for the polarization transfer. We allow that polarization transfer to occur for, say, 10 seconds. Then we switch that off adiabatically and detect the hyperpolarization in the Earth's magnetic field. And what you can see here is just a comparison between doing a SABRE hyperpolarized experiment in our 6.5 millitesla field, where we have about 5 millimolar of our catalyst and 80 microliters of our substrate, which in this case is pyridine, and 4 milliliters of our solvent, which in this case is methanol. And so we get a very strong signal in a single scan, and it's also very narrow because our sample is relatively small and the Earth's field is quite homogeneous. And this just compares to normal operation of this device, where you have to use a much bigger sample, so you get a much broader line, and you're getting much less signal and where you're just pre-polarizing using sort of brute force hyperpolarization. So if we're looking at something like pyridine in the Earth's field, we just get a single resonance for all of the protons because we have no chemical shift, but we can still use this signal to look at a little bit of what's going on. And so what I haven't told you yet is that when we do these SABRE experiments, we don't start with our SABRE active catalyst. We actually start with a pre-catalyst, and then we mix that with our target substrate and parahydrogen to form our active catalyst. So in this experiment, we're just doing a series of hyperpolarization experiments where at time 0, we've just injected the pre-catalyst and pyridine mixture into the reaction cell, and we start to bubble hydrogen. And so you can see an increase in hyperpolarization as we form more and more of the active catalyst, and then we reach a plateau when we have fully activated catalyst, and then we get highly reproducible hyperpolarization. So if we want to push this even further, we want to access those fields that I talked about that are below the Earth's magnetic field. So to do that, we need to actively cancel our Earth's magnetic field. And we can do this by adding a 3-axis Helmholtz coils to our system. And we use X and Y basically to correct for the fact that our Earth's field doesn't point vertically, it points at some angle. So we can just adjust currents through the X and Y until our net field is vertical. And of course, because we're doing NMR, our Larmor frequency gives us a very precise measure of what the net field is in our sample. So it's very easy to calibrate these measurements. And then once we've done that, we can then use the Z component to control the magnitude of the Earth's field and along Z, or the net field along Z. And so we can either increase it or decrease the overall field. And by looking at our tuning ranges at positive frequency and negative frequency, we can see that we have a very linear correlation, and we can actually really well define where 0 is. So one of the first things that we use this system for is to look at actually what's happening to the lifetimes of our SABRE hyperpolarization in these really low magnetic fields. Because if you remember, normally after we hyperpolarize, we take our sample and we move it through lots of unknown fields. So we're just interested in particularly what happens as we approach 0. So in these experiments, we're hyperpolarizing our pyridine like we did before in a 6.5 millitesla field. And then we're allowing that hyperpolarization to evolve in some microtesla field that we're controlling with our Helmholtz coil. And then we switch to a common detection field at 2,200 hertz, so essentially in the Earth's magnetic field. And by doing these experiments, we can look at what happens to our T1 values. So again, for pyridine, and we're looking at the difference between having a deuterated solvent and a protonated solvent. And what we can see is that we have a significant drop in the relaxation time as we approach 0, and that this is symmetric around 0 because, of course, it doesn't care whether our field is pointed up or pointed down. Interestingly, one of the questions about SABRE hyperpolarization that I often get a lot is what happens if you pass through 0 after you've hyperpolarized? And these experiments are showing that, so in these experiments here, we're passing through 0 twice essentially. And so when we're doing this quite quickly with the field cycling, we see some loss of overall signal, but we're certainly not losing all of our hyperpolarization by passing through 0. So moving on from just looking at a single peak from proton, if we want to use the system to explore more of the spin dynamics of what's happening in this regime, we need to introduce sort of chemical discrimination, and we can do that by looking at heteronuclei and where we have heteronuclear J coupling. So for Earth's field NMR, we're particularly fond of using fluorine because fluorine and proton are so close together, they're only 130 hertz apart, that we can detect them in the same spectrum. And so what I'm just showing here is that we can now choose to whether we hyperpolarize in the millitesla regime, in which case we're going to hyperpolarize the protons, or we can hyperpolarize in the microtesla regime where we don't turn on this field. We only let our hyperpolarization form in the very weak magnetic field, in which case we hyperpolarize the fluorine. So beyond just seeing the fact that we hyperpolarize one or the other, which is a well-known result, we can also then start to dig deeper into what's happening in this microtesla regime. And beyond just getting how much hyperpolarization we're achieving, we can also see in these Earth field spectra that we've got sort of a signature of what's being hyperpolarized and what magnetic states are being hyperpolarized. And through the use of simulations, we can start to understand, for example, here close to 0 field, we are hyperpolarizing only one of the protons in our molecule due to the relatively strong coupling between the fluorine and the proton here, and the weaker coupling to the orthoproton. So this just really provides us with a platform to start to look in more detail at some of these systems. And one of the advantages of doing this where we're not having to move our sample is that we can capture things that might have shorter lifetimes because the field switching is quite fast. It's on the order of milliseconds, although we do have a settling time of about 50 milliseconds. And so we can capture maybe some of these faster relaxing states to understand what's going on in these systems. So just to the last system I want to talk about is a bit different. So this is not technically SABRE anymore. So this is a different type of complex. So like the SABRE catalyst, maybe hard to see here, but this is an iridium catalyst. So we have iridium dihydride. And in this particular sample, we have a mixture of complexes with 2 phosphines and a complex with 1 phosphine. And then we have this DMSO coordinated trans to one of the hydrides. And if you take this sample, you fill it with parahydrogen and put it into a high field magnet, what you actually get is you get continuous hyperpolarization over a period of time until you run out of parahydrogen in solution. And you see very large hyperpolarization of the hydrides for both of these complexes and also some hyperpolarization on the DMSO. And so what that's saying is that this complex is constantly recycling, exchanging parahydrogen because of dissociation of the DMSO. And so what this was interesting for us to look at in the ultra low field regime is because then this gives us a chance to look not just at the sort of SABRE transfer to the substrate, but actually looking at what's happening to the hydrides that are coordinated to the catalyst itself. And now for these systems, we're really at sort of the edge of our signal to noise. But if we do a similar experiment to what I showed before, but in this top trace here, we're not actually putting on a polarization transfer field at all. We're just bubbling parahydrogen through the sample in the Earth's field, and we're just signal averaging, just like a normal NMR, over and over and over again for about 10 minutes. And we start to see these peaks that look very much like the hydride peaks at high field NMR, and they're separated by 35 hertz, which is the sum of these hydride phosphorus couplings. So this is clearly, we're looking at the complex with the 2 phosphines, and we're now seeing in the Earth's field the actual hyperpolarization from the hydrides themselves. Now, if we then do a more SABRE-like experiment where we turn on our polarization transfer field and then detect, we still see this peak at essentially at 0, and that is the SABRE transfer of the DMSO. So that's just confirming the fact that the reason why we're seeing this hyperpolarization is because the DMSO is dissociating from the complex that allows the parahydrogen to exchange, and then we get the hyperpolarization on both the hydrides and the DMSO. And so this work was all done by a PhD student, Eminata Saho, as part of the ZOLF NMR EU network. And so the goal here, we're really at the sort of edge of our sort of detection range here. And so the goal here is to shift this to potentially look in the ZOLF regime and use something like an atomic magnetometer to detect these kinds of systems so that we get much better sensitivity. And because we have this phosphorus coupling, we should be in a sort of potentially a detection range suitable for the atomic magnetometer. And I should say this work is also done in collaboration with my colleague Simon Duckett. So just to sort of conclude a little bit, what we've got, what we've been developing is kind of a platform for actually looking directly at what's happening to the evolution of the parahydrogen hyperpolarization in the ultra low field regime. And by choosing different sort of model chemical systems, we can probe different aspects of the experiment, from looking just at the proton polarization to looking at the interaction between protons and heteronuclei like fluorine. And then also with some of the systems I just described, we can actually look at the hydrides on the complex themselves. And this is all with relatively simple and cheap instrumentation. And because of the sort of the fact that we can just keep bubbling and keep renewing our hyperpolarization, we can do a set of experiments over a day on the same sample and really explore it in detail. By using the system, we've shown that when we develop where we create parahydrogen hyperpolarization, even when we pass through zero field, we're not losing all of that polarization, although there may be a time dependence there. Whereas if you do it more slowly, it might you might lose more. Like I was saying, we have this sort of new family of complexes, and Aminat has been looking at lots of different phosphines and lots of different complexes with different kind of sort of spin patterns. And so we can really use these to try and look at what's happening on the catalyst itself. And just to finish with some acknowledgements, the work I've showed today was largely done by my former postdoc, Fraser Hill Casey, and 3 current PhD students, Aminata, James, and Matthews. Also a lot of work done by project students over the years. Thank you to the funders, and thank you for your attention.
Thank you, Megan. Are there questions?
Phosphine work is extremely interesting. What sort of concentration of phosphine were you using for that one?
So the complex itself was about 10, on the order of 10 millimolar. Those experiments were done on, and there's different ways of creating that, whether we start with sort of a tris DMSO complex and then mix in the phosphine, and then you have various amounts where you might have, say, 2-fold excess of the phosphine to drive it to the form that you want. So, but 10 millimolar kind of concentration.
Do you have any estimates about the exchange rates for either the hydrogen or for the DMSO?
Yeah, so we've measured all those things, and the exchange rate is really crucial because it needs to be in the right sort of time so that you have enough time to build up the hyperpolarization, but you're not so some that exchange faster will deplete your parahydrogen reserves quite quickly. And then of course also when you're detecting in the Earth's field, the decay is more about the exchange rather than say your natural T2 decay. I think so. Some with faster exchange decays quite quickly in the Earth's field, so we get quite broad lines.
Right. The question I asked is, do you know what the rates are? And I guess the answer I wanted wasn't yes, but a number.
Oh yeah. So those ones are about 3 per second, I think.
For the DMSO or for the hydrogen?
For the hydrogen.
Okay.
The residence time is about 200, 300 milliseconds.
Okay.
Like
Thank you. Very interesting work.
Thanks for the nice talk. How much of the relaxation near zero field is from scalar relaxation of the second kind, and can you get rid of it if you use nitrogen 15 instead of 14?
Yeah, so I mean, I'm not an expert in relaxation, so I can't get a definitive answer, but I would strongly suspect that the effects you're seeing near zero field would be things like the quadrupolar effects, so nitrogen 15 might help. And yeah, so but this would be a system where you could test that quite robustly.
Okay, thanks.
All right, any further questions? I'll ask a question actually. The Earth's field systems, the polarization coil that you're using for your polarization transfer might not necessarily be optimized for homogeneity. It's sort of a brute force field. And I'm just wondering if that matters for you and how close that has to be to 6.5 millitesla. Yeah,
so it's sort of like 10% homogeneity, so you can't do NMR in it. But the sort of resonance condition for SABRE around 6 millitesla is quite broad. So 10% is actually quite a homogeneous field. And also our sample's reasonably small. So if you think that normally we shake in the fringe field of the magnet, which is much, much worse, it's actually, for those purposes, pretty reasonable, although obviously if you tried to detect the NMR, that would be problematic.
Thanks. Right, please join me in thanking Megan again.
Is Marie-Josée Ferre?
from the University of Florida. The title of her talk is A Hybrid Lac Inept Approach for Highly Efficient Spin Order Transfer in Sidearm Hydrogenation with Parahydrogen.
All right. So good morning, everyone. So thank you for the introduction. And I would first like to start off with hyperpolarized pyruvate. So hyperpolarized pyruvate is a versatile biomarker for metabolic processes where the conversion of hyperpolarized pyruvate to lactate has shown to be a useful tool in cancer diagnosis as well as treatment response. However, the 10% C13 polarization is needed for in vivo imaging of pyruvate. Now, there are many ways to make hyperpolarized pyruvate. The commercialized technique to date is DNP. However, there are quite a few drawbacks to DNP. It's slow, expensive, not easily accessible to everyone, and the list goes on. However, parahydrogen-based hyperpolarization provides a inexpensive and fast alternative to creating hyperpolarized pyruvate, the non-hydrogenative route being saber sheath. However, this method uses methanol as a solvent, and catalyst separation is challenging. As for the hydrogenative route, hyperpolarized pyruvate has been accomplished via sidearm hydrogenation, where a unsaturated precursor is attached to the metabolite of interest. This can then undergo hydrogenation with parahydrogen. This polarization can then be transferred to the C13 on the metabolite of interest, where then the sidearm can undergo cleavage and phase separation. Now, polarization transfer has been accomplished for hydrogenation at low field by field cycling. However, there is a limited absolute C13 polarization. Now, for hydrogenation with parahydrogen at high field and detection at high field, polarization transfer has been accomplished via inept-based pulse sequences. However, there's limited space in the magnet bore for our ultrasonic spray injection reactor system, which I'll explain a little bit more later. So this polarization transfer method for our purposes doesn't really fit the bill. Now, there are generally two types of sidearms used for sidearm hydrogenation. There is vinyl and propargyl. Now, when propargyl undergoes hydrogenation, it will form an allyl sidearm. Now, you can see that there's an intervening carbon between the double bond where parahydrogen has been added to the C13 on the molecule of interest. So this actually makes the GA coupling very small, so a direct polarization transfer can't be achieved in this manner. This is a two-step process then to transfer that polarization. However, the benefit of using this propargyl sidearm is that it provides a faster reaction rate for conversion, which creates more hyperpolarized product. And this has a faster rate than that of the vinyl sidearm. However, the vinyl sidearm has a large enough J coupling where it can undergo direct polarization transfer in one step. Now, to transfer polarization at high fields, there are, depending on what sidearm you're using, you can use a different type of pulse sequence. So for example, the propargyl sidearm, we can use proton relayed sidearm hydrogenation, where we are using a relay proton to shuttle that parahydrogen polarization to the C13, and this is a two-step process. Now, they reported 100% theoretical efficiency if we are ignoring the long-range J coupling involved. And they were able to experimentally observe an efficiency of 46% with a 7% C13 polarization pre-cleavage of the sidearm. Now, if we were to use a vinyl sidearm after hydrogenation, this can undergo direct polarization transfer in a single step by Minerva. They reported an 100% theoretical efficiency, but if one of the couplings is disregarded, they also have an observed experimental efficiency of 80% with a 60% C13 polarization pre-cleavage. Now, I would first like to introduce one of our newly designed pulse sequences called Altadena Selective Inept. So this is specifically for the vinyl ester sidearm. So the experimental design is We use our ultrasonic spray injection to create bulk hyperpolarized substrate. This can then undergo adiabatic passage to have a hyperpolarized altadena type molecule. We can then use our selective inept pulse sequence to transfer the polarization from H2 directly to the C13 of the metabolite of interest. Now, our simulations have shown that we have a 96.2 theoretical efficiency, regardless of our J14 coupling. So this is actually a higher theoretical efficiency than previously reported high field polarization transfer inept-based techniques. Now, switching gears back to the propargyl sidearm. So during hydrogenation and altadena hydrogenation experiment of propargyl acetate, I obtained a hyperpolarized allyl acetate spectrum. Now, on the spectrum, we can see that protons 1 and 2 show a net alignment type line shape, which is agreeing to the altadena experiment. However, we do notice that we have some significant amount of polarization showed on protons 3 and 6. So we found that there's 2 reasons why this could be happening. So first, the polarization on H3 and 6 is due to an adiabatic passage through a level anti-crossing on J23, which I'll talk a little bit about later. But also, we wanted to note that we found that there's significant losses because of proton 5. And this is due to the large J coupling between 2 and 5 being significantly larger than the J coupling between the 2 parahydrogen protons. So what's happening is when we project the parahydrogen singlet onto the proton eigenstates of allyl acetate at low fields, we are actually then inducing coherences of J25, which then cause significant polarization losses after kinetic averaging. And we found that this loss can be mitigated by selective deuteration of proton 5, which I am showing here in our Lacadena simulations, where our red spectrum is non-deuterated allyl acetate, and our black spectrum is per-deuterated allyl acetate at positions 5 and also one of the relay protons of the sidearm. Now we can see that there's a significant increase in intensity of protons 2 and 3. So this is because now the parahydrogen singlet order is conserved because of that deuteration of proton 5. So now when this undergoes adiabatic passage and we have a level anti-crossing, then we get actually a very efficient transfer of polarization to that relay proton. Also just noting that we have another molecule where let's say that the chemical shift at that relay proton is now in between the parahydrogen protons. We actually don't exhibit this level anti-crossing effect. So there's no proton polarization shuttling to that relay spin. So this is showing that this level anti-crossing effect is really sensitive to the design of the sidearm. And just recapping, no polarization is shown here. Okay, so now talking a little bit more about this level anti-crossing effect. So we're experiencing a proton shuttling effect during adiabatic passage through a level anti-crossing. So for an idealized AMX spin system consisting of 3 protons, where 1 and 2 are coupled, 2 and 3 are coupled, but 1 is not coupled to 3, we can now refer to our eigenvalue correlation diagram, where the green balls are populations originating from parahydrogen. So in our first construct, where delta 1 is greater than delta 2, which is greater than delta 3, we can see that we do have a level anti-crossing effect, meaning that proton shuttling is occurring and the polarization from the first proton is getting transferred to the third proton. We also wanted to see what happens when we turn that J23 coupling off, and we actually don't experience a level anti-crossing effect. So in this case, we would most likely expect a typical net alignment Altadena spectrum without that polarization sharing of the relay proton. Now, for construct 2, remember where we had that the chemical shift of that relay proton in between the parahydrogen protons, we then experienced, or actually we didn't experience a level anti-crossing effect, regardless if that J23 coupling is on or off. And this is just a chart to sum up what the previous slide was saying, that in case our construct 1, we do experience that level anti-crossing, and spin order from that first proton gets shuttled to the third proton or the relay proton for a spontaneous and complete transfer. And then construct 2, we didn't experience a level anti-crossing effect, meaning the polarization stayed on those two parahydrogen protons. Now, to experimentally test this, we use our ultrasonic spray Altadena system. So I'm only going to briefly go over this. I do have a poster on this set up today and Thursday, so feel free to stop by. I'd love to chat about it. But here we use a syringe pump to infuse our precursor solution through a vibrating ultrasonic nozzle. This then gets sprayed, our product then gets sprayed into a pressurized chamber of parahydrogen, where then we have hyperpolarized product. We then use a withdrawing syringe pump to withdraw our hyperpolarized product through adiabatic passage at a constant rate to high field at our 400 megahertz variant flow probe. Now, presenting our polarization transfer pulse sequence, Lacadina selective inept. So this is specifically for propargyl ester sidearms, but the beauty about this is that we're still actually using the same pulse sequence. The only thing that we have changed is now we are using this side arm of propargyl acetate that gets hydrogenated, undergoes rapid adiabatic passage, and we have that spontaneous proton polarization shuttling to the relay protons. So we can use actually our selective inept to selectively transfer this proton, or this relay proton polarization to the C13 on the metabolite. Now, our simulations have shown that we can get 82% theoretical efficiency with this whole process. Now, to experimentally demonstrate our Lacadina selective inept pulse sequence, we hydrogenated d-propargyl pyruvate with 99% parahydrogen, a rhodium catalyst in acetone D6. We then acquired a hyperpolarized d-allyl pyruvate, where we then use our Lacadina selective inept pulse sequence to transfer the relay polarization to the C13 of the pyruvate. We then were able to acquire a hyperpolarized C13 spectrum, and we're able to measure a C13 polarization of 4.6%. Now we can get 2 times the C13 polarization upon partial deuteration of this relay CH2 group, which then would put us about 9.2% polarization. We also tested the non-deuterated propargyl pyruvate sort of as a baseline polarization. So undergoing the exact same conditions on the previous slide, we were able to have hyperpolarized allyl pyruvate after hydrogenation with parahydrogen. We then used the Lacadina selective inept pulse sequence to transfer this relay proton polarization to the C13 on pyruvate, and acquired a C13 polarization of 2.11%. Now, just to summarize what we went over. So we introduced a new Altadena inept method for spin order transfer on vinyl ester sidearms that showed a 96% theoretical efficiency, even when we include J13 in our simulations. Also, we introduced a new Lacadina-Annette method for spin order transfer in propargyl esters. Now, we also showed the spontaneous spin shuttling via adiabatic passage through level anti-crossings. And the increased polarization can be done by selective deuteration of the sidearm to make this level anti-crossing proton shuttling more efficient. And also briefly introduced a new ultrasonic shuttling system. So that will help facilitate upscaling of hyperpolarized metabolite production. Now, future improvements. Now, we would love to do experiments on per-deuterated vinyl sidearms and polarization transfer with Altadena Annette. The single deuteration of that relay carbon will give us that 2 times gain in the selective Annette deficiency. And incorporation of multiple pi pulses will actually help improve the chemical shift refocusing in our inept pulse sequence. And of course, always the use of faster experimental transfer will give us a better starting polarization. Now, I would like to acknowledge Dr. Bowers and my lab mates, which they are also giving posters at ENC, so feel free to check those out. I would also like to thank Dr. William Hale. So he helped me with the original design of the spray injection system. And I would also like to thank our collaborators, Dr. Alex Grenning and Dr. V. Dong and their graduate students for helping us with hydrogenation precursor synthesis. And I would also like to thank University of Florida and NSF and the National High Magnetic Field Laboratory for funding. And with that, thank you for listening and happy to answer any questions.
All right, thank you. Are there questions?
I think that's very inspiring how you combine hardware with chemistry and pulse sequences.
Oh, thank you.
Into one unit. Maybe you mentioned it and I missed it. So you have the side chain hydrogenation of the C1 of pyruvate with the side chain.
Yes.
And the idea is eventually I had the impression the idea was to see what happens to pyruvate in a biological setting. So eventually that side arm has to come off.
Right.
So, but you need a high field in order to do your selective transfer.
Yes.
So when will that site, I mean, would that transfer be happening inside an MRI or an NMR, and then it would come off inside the high field, or what is the end goal of the game?
So ideally, yes, we want to try to cleave off the sidearm. There's actually been a recently designed method where you can maintain that polarization that's on C13 and undergo cleavage in a recent paper, actually. So that does involve taking the molecule possibly out of the magnetic field, but it used actually magnetic disks to maintain that polarization during cleavage where it can get transferred back in. So that might be something that we could think about integrating at a later point in time. But yes, the sidearm definitely does have to be cleaved off at some point, and we do want to maintain as much polarization on C13 as possible.
Thank you very much for the very nice presentation. I just was curious, one of your conclusions was to try to make the transfer faster and getting it faster to be detected. Can you just comment on your current timings, like how long it takes from preparation to detection?
For Kermit, so the whole process takes about, with hydrogenation to get that bulk hyperpolarized production, and transfer, it takes about 12 seconds. The transport time takes 6 seconds to the high magnetic field. So these experiments were very modest initially. So we have plenty of wiggle room to basically have a faster withdrawing flow rate into the magnet as well. So ideally, we also need to think about preserving that adiabatic passage, because that process also needs to be optimized as well, which we're also trying to play around with that when we're also changing the flow rate. So it's a balance.
All right, please join me in thanking Maria Jose again. Okay, our next speaker is Shannon Erickson from Duke University. The title of her talk is Non-Intuitive Modulated Fields Improve Polarization Transfer in Saber.
Hi, so thank you very much for that introduction. My name is Shannon Erickson. I'm a graduate student in Dr. Warren's lab at Duke University. And today I'm going to be talking with you about using new physical insights to further optimize saber sheath polarization transfer. Specifically, I'm going to be going through two field sequences that we use to generate these two plots that I'm showing here, where this one over here is using a two-field sequence, which can give us a signal gain of up to 3-fold over continuous field experiments. And this one over here is a multi-axial pulse sequence, which allows us to decouple our catalyst from our target nucleus from our hydrides while the catalyst is exchanging its ligands. And that can give us a signal gain of about 2.5-fold. I'm obviously going to get into more of the details on these plots later on in this talk. But for now, the message that I want to get across is that all of my data, experimental data that I'm collecting, is going to be displayed as these points. And then I will have simulations that will run under the exact same conditions that is going to be overlaying that with a solid line. These numerical simulations is from a package that I actually presented at ENC 2020. And we've been able to do some really nice work with that package during that time. So first, I'm very lucky to have gone after someone who already gave a saber talk, so I'll be very brief in introducing this topic, but signal amplification by reversible exchange is essentially a hyperpolarization technique which uses parahydrogen as a source of spin order in order to push population into a magnetized state on a target nucleus. In order to do that, we bring our parahydrogen and some thermally polarized target nucleus into transient magnetic contact on an iridium catalyst, like that one shown here, which initially populates our singlet state on our hydride to give us about 50% singlet hydride with alpha on our target nucleus and 50% singlet hydride with beta on our target nucleus. We then apply some strategic field conditions, which allow us to target population transfer out of one of those states and into a state that has a spin flip on the target nucleus. So here I'm targeting that singlet alpha into a T plus beta state, while suppressing the transition out of that singlet beta state in order to increase our population in that beta state on our target nucleus. Because this is a reversible interaction, we are then able to replenish our initial state through chemical exchange and then repeat this process many, many times for ligands in solution. So here I want to introduce the chemical complex that we're going to be using for majority of our experiments and simulations moving forward, where this is our iridium catalyst. And I've truncated off these axial ligands because they're not incredibly important for the purposes of this talk. But in these equatorial binding positions, we have our parahydrogen associated over here, a target compound, which is here 15N-acetonitrile associated here with that 15N labeled nucleus directly binding with that catalyst, as well as a magnetically silent coligand here in 14N pyridine. So there are two continuous field conditions that we can use to generate either positive or minus polarization. And this polarization buildup has traditionally been explained using a level anti-crossing or avoided crossing picture. So we're going to take a look at one of the transitions for this complex, where we're going from singlet alpha into T plus beta under the field condition at this peak up here. So first, let's take a look at the nuclear spin Hamiltonian for this system. I'm truncating off those methyl protons just for the simplicity of discussion here. But we have our Larmor terms for our hydride nuclei over here with this I1Z and I2Z terms. We have that same term for our nitrogen nucleus here with this LZ term. Then we have a coupling between our hydrides with that JHH coupling shown in red. And we have a coupling between this trans hydrogen to our target nucleus here, which is shown by this JLH coupling here, or JHL. There is a very, very negligibly small coupling between this hydrogen here that's bound 90 degrees to our catalyst, and it's so small as to be negligible, so I truncated it out of the Hamiltonian here. So if we want to just look at our target states of interest, and this is a Hamiltonian that is so simplified as to be technically incorrect, but I'm essentially just showing you our singlet alpha and T plus beta target states, where we want to look at how that field is actually influencing population transfer between these two states. So we see that they are coupled together by these J coupling terms here, and that the population difference between these two fields is dependent on the magnetic field through those Larmor terms that I was just talking about. When we bring these energies close together under this, or we approach this lat condition, which for this singlet alpha to T plus beta is shown here. If we want to target the opposing spin flip, we can use an oppositely signed magnetic field, and we can transfer population in the opposite direction in a different manifold. But this was traditionally where we were sitting in terms of explaining how Saber population transfer was occurring. It's this en masse passing of population between these states at an avoided crossing. But unfortunately, there are some assumptions that get made that end up breaking down and not actually predicting optimal experimental values for us that we are trying to address here. So if I plot that level anti-crossing matching condition for this particular spin system as a function of the J coupling between our hydrogen nucleus and our target nitrogen, that polarization maximum should be occurring at this black line that I'm showing right here. But when we simulate this system with an exchange rate of 10 per second, we actually see that optimal polarization transfer field under simulation is greatly diverging. And even under those experimental values for that J coupling for canonical systems like 15N acetonitrile and 15N pyridine, which tend to be in that -20 to -25 hertz range, we see that there's actually a dramatic difference between these two values, which has actually been experimentally measured since the inception of Saber, because majority of the polarization transfer maxima are measured to be around -0.3 to -0.6 microtesla, which more closely agrees with these simulated experiments as opposed to that level anti-crossing condition. I also want to note here, and I'm going to come back to this idea, that in this experimental regime for those J couplings, the polarization that we're generating at that optimum is actually very suboptimal in terms of what we would be able to generate at much lower J coupling values. So keep this in the back of your mind because we're going to return to this idea later. So let's look at designing some pulse sequences around this level anti-crossing matching condition. We can basically take our optimal polarization transfer condition for a continuous field experiment, and then we're watching as our polarization is building up over time in this plot over here. And we can generate a good amount of polarization using that plot at that specific continuous field condition. But what do we expect if we're proposing to apply a pulse that looks like this, where essentially we're applying a 0 microtesla field for 3 milliseconds, which is not predicted to generate polarization. Then we're moving to a much higher field at -22.35 microtesla, which is also a field condition that is not predicted to produce polarization. On average, we're at around -18 microtesla, which again is not predicted to produce polarization. So now I'm proposing a pulse that is not either instantaneously or on average predicted to generate any polarization transfer. And if this enormous white space on the top of my plot didn't give it away already, we actually generate far more polarization under these conditions than we do under that continuous field experiment, and up to 3.2-fold increase under numerical simulation. So I'm going to take a quick step back to better explain what is actually going on in this pulse that we're proposing. And now I'm going to be applying this pulse sequence up here. I apologize, it looks like some of my figures got compressed. But we're having that 3 millisecond 0 microtesla pulse that's still being applied, and then we're following it by some arbitrary interrupting pulse that has some field strength VD along this axis here, some field duration tau D along this axis up here, and I'm plotting the polarization after multiple applications of this pulse. Under that traditional level anti-crossing based explanation for Saber polarization transfer, our expectation would be that we will be passing polarization into our target state under conditions where our average field over the course of this pulse is close to that optimal continuous field that we talked about. And that condition is plotted by this white line that might be very difficult to see, but we do see polarization build up around that condition. But when we actually perform our numerical simulations on this pulse sequence, we see polarization buildup at fields that are very far from that level anti-crossing matching condition and very far from that continuous field optimal way out there. And we see these sharp resonance bands that are centered about conditions over the course of our pulse that induce a phase shift that is close to 2 pi or multiples of 2 pi between our nitrogen and or proton frequencies over the course of that pulse. This is very easy for us to verify experimentally. We can either hold our field constant and sweep through that pulse duration, and we can see very excellent agreement between our theory and experiment. Or we can hold our pulse duration constant, sweep through our field. Once again, we get very excellent agreement between our theory and experiment. So this is a real effect that we are seeing here. But now we need to take another step back and say, why are we actually seeing this happening and what is going on with this? So returning back to our continuous field condition, let's take another look at how we're pumping magnetization from a slightly different perspective. So here I'm showing our low field Hamiltonian again. I'm breaking out those J coupling terms into its transverse terms with those XX and YY terms, and then its longitudinal term ZZ. Now, instead of thinking about this as an en masse population transfer between two states, let's instead take a look at this sequential interactions with our Hamiltonian using perturbation theory to look at how spin operators are actually being pumped in our system to take us from singlet order parahydrogen, which is shown here as this I1.I2 term, all the way out to direct magnetization on our target ligand, which is shown as this LZ term. So the way to read out this plot is we're essentially looking at higher and higher order terms in our in perturbation theory after sequential interaction with different terms in our Hamiltonian. So we start with this parahydrogen term, and to generate our first order spin operator term, which I'm only showing one as an example here, there are many other terms that just look like this. But interaction with that J coupling term will give us spin operators that look like this, that will grow in linearly. And then we can have an additional interaction with our Hamiltonian under either that delta omega HL term or our JHH coupling. And that will give us spin operators that look like this, which grow in quadratically. And then we can keep progressing through that spin operator pathway until we can actually see direct magnetization on our target ligand or target nucleus, which will grow in as T to the fourth. There are two important takeaways from this spin operator pathway picture. The first is that we're actually only using the transverse terms of our J coupling there to provide the necessary rotations to take us from singlet state to direct magnetization. And the second is that that delta omega HL term is essentially just acting as a phase shift along that spin operator pathway. And I'm going to pull out these spin operators just to more easily see that, where we're basically taking a term that looks like 1x LX and going into a minus I1x LY term. So we're giving ourselves a little phase shift between those two spin operators using that delta omega HL term. So this can help to explain why we're seeing that banded structure that are centered around that is highly dependent on that phase shift between our nitrogen and proton frequencies. But I still haven't explained why we're seeing this improvement in polarization over the course of that pulse using this specific pulse sequence. And that's actually a little bit easier for us to take a look at if instead of looking at the instantaneous Hamiltonian, we look at the average or effective Hamiltonian over the course of that pulse packet. So what I'm doing here is we can use the applied field to generate a toggling frame and then take the 0th order average to get the effective Hamiltonian over that full pulse packet. I'm obviously sweeping a lot of the math and derivation behind this under the rug. If you're interested in that, you can either come and talk to me at my poster, or you can take a look at our recently published paper here in this corner. But we can generate this effective Hamiltonian and then interrogate what's going on with this system. And the important takeaways for this generated Hamiltonian here are that we are I don't know how well that's actually showing up, but we are preserving our transverse terms for that JHL there down in this top term, which is modified by an M0 coefficient. And we are also generating this these phase shifted transverse terms, which are modified by this N0 coefficient. What's important to note about these two coefficients is that they're highly dependent on the phase difference between our spin operators for our proton and our nitrogen. So now we have this effective Hamiltonian for this pulse packet, and we can use perturbation theory again to take a look at how we are progressing from singlet order parahydrogen into direct magnetization. So we essentially have eaten that phase rotation under that delta omega HL term into one of our two terms for that JNH coupling here. So we essentially have to rotate under one term in the J coupling, and then we can rotate under the phase rotated term, and we get the same exact effect as we do from that 4-step process that I presented for the continuous field. Again, we have a couple of things to note here. So M0 and N0 end up actually tending to, or going to 0 when our phase rotation is at multiples of 2 pi n, which makes sense because we're essentially just rotating our system back into an initial condition. And that's why we end up seeing these stripes of 0 with those resonances centered about that 2 pi n condition. The second thing to note is that M0 and N0 are inversely proportional to the total phase rotation over the course of our pulse, which means that we can effectively attenuate that J coupling by reducing that M0 and N0 term by giving a large degree of phase rotation over the course of that high field pulse there. So that ends up giving us these improvements in polarization transfer that we saw under that long high field duration pulse at the very beginning. So now polarization transfer is improving at lower values of JHL. Long high field interruptions are decreasing that effective JHL, so we can use pulse sequences that look like this in order to get improvements in polarization transfer of up to 3-fold, which we're seeing from this baseline Saber sheath measure on the same sample that was used to generate some of these higher polarizations. Unfortunately, because that phase rotation needs to be very specific in order to induce polarization transfer, homogeneity becomes very important for a pulse shape like this. If we even have a 2% shift in our field, we can go from this positive peak down to this negative peak, and we would average out to get 0 net polarization transfer. We can use a very simple field reversal halfway through that high field pulse in order to compensate for those inhomogeneities though, which will still preserve that attenuation of the J coupling term and preserves that precise rotation that we need in order to pass polarization onto our target. So now I'm going to shift gears a little bit, and I'm going to talk about these multi-axial pulse sequences that we've been applying at low field to more efficiently generate polarization. And this is going to be starting with our coherently pumped Saber sheath experiment, which will essentially, we published this in 2019, and what we do with this is we sit at that low field continuous field optimum condition for some amount of time in order to allow polarization to build up in our system, and then we move far away to a resonance condition or to an off resonance condition which halts that polarization transfer. What that looks like for our nitrogen polarization over time is shown on this plot here, where we have a sharp increase in polarization, and then we flatline for that full delay pulse, and then we have another sharp increase in polarization. That delay field is set there so that we can reinitialize our complex, so rebind fresh parahydrogen and a new target ligand in order to reinitialize for the next evolution field pulse. The problem that we're trying to address here is that every time that we're binding a new singlet parahydrogen into our complex, we're essentially unlocking that singlet state with the J coupling to our target nucleus. So we start to evolve out of that singlet state immediately after binding, and we're losing singlet order over the course of that delay field. There's a very simple fix to this, is to remove the coupling. We're not breaking the symmetry if we remove that coupling, and decoupling is something that has been done for a very, very long time. It's already well in use for FIP experiments. And we can essentially either irradiate on our nitrogen nucleus or our target hydrogen nucleus in order to prevent that J coupling from communicating between those two states. We irradiate on our nitrogen nucleus, then we're essentially polarizing and then crushing our polarization, and then polarizing again and crushing our polarization, so slightly suboptimal for us. So we would target our hydrogen nucleus, which allows us to polarize and then preserve that singlet state over the course of the delay field, and then basically give us more efficiency per pulse by initializing our state more optimally. We can see this very easily experimentally by just setting our field conditions and then sweeping through our frequency, where we do get this dip in polarization transfer efficiency at omega and our Larmor frequency for our nitrogen, and we get an increase in polarization transfer efficiency at that hydrogen frequency there. I do want to give a very quick plug for my colleague who is doing some more work with oscillating that leading field. So Xiaoqing Li has been looking at some of these simple arbitrary oscillating pulses to manipulate the Hamiltonian for more optimal transfer. She can use either a very simple square pulse with set conditions, a low offset and a period in order to get this polarization improvement for threefold, where we still see excellent agreement between theory and experiment. But unfortunately, we do see that we can fully attenuate that J coupling term and crush polarization under certain conditions. And interestingly, we can actually use a pulse shape with less symmetry in order to avoid going into those nodes. So we can get this polarization transfer improvement and excellent agreement with theory and experiment across a broad range of potential pulses. And with that, I will leave up the summary slide for people to peruse. I do want to point out that my colleague, Dr. Jake Lindale, is presenting poster 85, which is discussing those numerical simulations that I've been presenting. Xiaoqing Li is at poster 86, which will be presented today and Thursday, and I am presenting on using those oscillating fields to, instead of targeting a magnetized state, actually targeting a field-independent singlet state, and that's at poster 103, and I would be happy to discuss any of this with anyone. Thank you very much.
Thank you, Shannon. We have time for a quick question. Matt?
Great work and a tremendous presentation. So you commented how slewing these magnetic fields, you need to be rather careful experimentally. Have you thought about going into like a rotating frame with spin lock pulses, doing the same experiments, but just with RF?
Yes. So are you talking more about the those decoupling pulses at the end there, or about the square pulses that I was talking at the beginning?
About anytime you're trying to match the magnetic fields tailored very carefully to
Yes.
get these conditions right. You should be able to just do that with RF.
Yeah, so the problem with radio frequency irradiation for the fields that we're using here is that for majority of the time, we're overlapping our nuclei right on top of each other. The only reason that I was able to selectively irradiate on one of the nuclei for the decoupling pulse is because I lifted our field up to a condition where I'm separating those frequency out. So it is a little bit difficult for us to kind of selectively irradiate at these low field conditions.
Hey, Shannon, great talk. Still trying to get my head around this idea that, smaller effective J is better.
Yes.
I'll probably ask you more about that later. What does that say about what structures or J coupling networks might be more amenable to this, where you get a bigger enhancement by doing this pulsed approach as opposed to not getting a much bigger effect from just continuous field saver?
Yeah, so that is a great question. So the reason that attenuating that J coupling is giving us some of these higher polarizations is because we have an exchanging system. And when that system is living for longer than kind of an optimal pi pulse of transferring polarization into those magnetized states, we start to back pump. So if our J coupling is large enough, then we're essentially kind of averaging over these oscillations instead of constantly kind of growing in our polarization over time. So we've decreased that J coupling, we're constantly pushing polarization out onto our nucleus instead of back pumping and kind of getting this averaging out effect. What that does mean is that for compounds that have a smaller J coupling, if we reduce it further, we're not really doing all that much. So if you already have you're sitting in that optimal J coupling range, it's very difficult for us to further optimize where that J coupling is by attenuating it further. So that's a very great point. Yeah.
Very nice talk. I was wondering what is limiting the efficiency, or what is the theoretical efficiency for the converting I1.I2 into LC, this approach?
That is a great question, and I could talk about a lot of different aspects to these experiments that are kind of limiting that efficiency of polarization transfer there. I think that one of the big, so if we just look at the bound species, it's very easy for us to get a high degree of polarization transfer from our singlet state out onto that target ligand. The problem is that it's not just that bound species. We have our bound species as well as a bunch of free ligand that's off in solution. So we have about 20 times as much free ligand as we have bound nucleus. So we can transfer polarization with a high degree of efficiency. That ligand will pop off and be in solution now, and then we bind another ligand. So we can start transferring polarization onto that ligand, but this guy is out here in solution and he's already relaxing out here. Yeah.
One last question.
So I guess my question is a little bit related to your final comment. Great talk, beautiful Hamiltonians, but these times are very long. You're talking about 10 seconds, several seconds. And in this time, you have the exchange process and you have relaxation process. And relaxation can build up differentially from the two, the two spins are not at the same distance. In 10 seconds, they can also cross-relax with the nitrogen and build up that polarization. So where do all these stochastic processes come into your picture?
So actually, if you do want to know more about that specific question, my colleague, Dr. Jake Lindale, has done extensive work with looking at some of these, incorporating these stochastic processes into a continuously oscillating quantum dynamical system, which has substantially helped us to very accurately simulate all of these processes, which are happening on the same timescale with a high degree of accuracy, which we have been able to verify experimentally across the board.
Poster 86 that you mentioned?
So Jake is at poster 85.
Please join me in thanking Shannon again.
So can you see it? Okay.
Okay, our next talk will be given by Shuyan Tang from the University of Minnesota. And the title of her talk is Ultra Low Frequency EPR using Longitudinal Detection and Fictitious Field Modulation.
Hello, everyone. Thank you for the opportunity. Today, I want to give you a brief introduction on a portable electron paramagnetic resonance system we built. First of all, EPR is very similar to NMR or MRI, except that we're detecting signals from unpaired electron spins. So there are a lot of commercially available EPR systems in the market. However, conventional EPR cannot measure spins with short relaxation times at low fields. But those signals are important for applications like low field imaging, material calibration, relaxometry. So our goal is to build a low-cost portable EPR system that can measure electron spins with short relaxation times at ultra-low fields. Here's a picture showing what our current setup looks like. It achieved everything I described before and is tabletop portable. To build a system like that, we combined longitudinal detection with fictitious field modulation. And I will start with longitudinal detection. In other words, Z-axis detection. Most of you are probably familiar with the transverse detection widely used in pulsed EPR or MRI, which means both the transmit and the receive coils are on the XY plane. And before acquisition, the transmit needs to be turned up first to avoid huge leakage. This leads to instrument dead time, and the fast decay signal at nanosecond or picosecond scale would just disappear during that. We're using longitudinal detection. Our receive coil is along Z-axis and is 90 degrees to our transmit coil. They're also tuned to different frequencies, usually more than 10 times apart. The combination of geometric isolation and frequency separation enabled us to do simultaneous transmit and receive and with a -80 dB isolation and get rid of the instrument dead time. To induce the longitudinal signal that's going to be picked up by our detection circuit, I proposed the fictitious field theory. We found in literature that even when the static polarizing field B0 equals 0, an XY plane RF field alone can polarize spins along Z-axis. I made an animation to show it. The blue arrow is the RF field that's going to rotate on the XY plane. And when I play the animation, you will see a red magnetization gradually grows. In the steady state, there will be a stable MC. It's like having a fictitious polarizing field along Z-axis generated by the RF field. I define it as B fictitious. This phenomenon cannot be explained using the standard Bloch equation. It assumes that the spin lattice relaxation is always going to along B0. And if there is no B0, there is no MZ. I want to mention that because at low fields, both spin lattice and spin relaxation times are assumed to be the same. So we can use a single parameter tau to represent both of them. And at low fields, we need to use the modified Bloch equation to simulate, which assumes that the spin lattice relaxation is going to be along the vector sum of both the RF field and the B0 field. Based on the modified Bloch equation, I was able to derive the value for the fictitious field. It is determined by both the RF field frequency and the amplitude. So by modulating the RF field, we're modulating the fictitious field to get Z-axis flux change and the longitudinal signal we want. Indeed, we have experimentally measured the longitudinal signal of iron oxide nanoparticles using fictitious field modulation. Even when B0 equals 0, there is a relatively strong signal right at the modulation frequency of the fictitious field, which shows that the fictitious field exists and is effective in polarizing spins. I want to mention that we built a Z-axis coil to cancel out the Earth's magnetic field, so the signal was induced by the fictitious field alone. Here's a picture showing the diagram I draw for our system. It is divided into 3 main parts: the B0 coil circuit, transmit coil circuit, and the receive coil circuit. You can easily tell that the transmit and the receive coil are 90 degrees to each other. By using different versions of this system, we were able to achieve 3 different applications: spectroscopy, imaging, and relaxation time measurement. I will only focus on the 3rd application in my talk today, but I do want to mention our collaboration with the UMM Bioheat and Mass Transfer Lab. They're loading red heart with magnetic nanoparticles before cryopreservation so that later they can use the hyperthermia generated by those particles to rewarm the heart for implant. But they're having trouble measuring the concentration of those particles in organ. So we're using the first 2 applications of our system to help them build a concentration map to improve the hyperthermia uniformity and efficiency. Here are some preliminary data for the concentration measurement, and they do look promising. So now I want to talk about how we do the relaxation time measurement. Relaxation time is a pretty important parameter in DMP MRI contrast agent design hyperthermia modeling. But people haven't been able to measure short relaxation times at low fields. So they just use the high field value for low field modeling. This is very inaccurate because relaxation time is not a fixed value and it changes with field strength. Using our method, we can measure it. Based on the fictitious field theory, I derived an equation which shows that if we do a frequency sweep spectrum on a material, the spectral peak will not occur at the Langmuir frequency people are used to. Instead, it is affected by the relaxation time. And according to this term, the shorter the relaxation time, the bigger the peak shift. Here's a picture showing the simulation I did on 3 different relaxation times using the modified block simulator I built. The dashed line marks where the Langmuir frequency is. And according to the simulation, the shorter the relaxation time, the bigger the peak shift. This fits the prediction of this equation. And this is different from the chemical shift because this peak shift was derived purely from the modified block equation and is caused by the relaxation along the RF field. And if we keep all the other parameters fixed and then do a frequency sweep spectrum, we can calculate the relaxation time back from the spectral peak shift. To experimentally measure the relaxation time, we built a frequency sweep system based on our existing AOD EPR system. We made major modifications to the transmit circuit, changing from a tuned one to a broadband frequency sweep one. Our first experiment is to measure the relaxation time of DPPH, a standard EPR material with a relaxation time at nanosecond range. So our frequency sweep is between 2 and 8 megahertz. The sweeping bandwidth is 6 megahertz, which is pretty big compared to the center frequency 5 megahertz. So we put a lot of efforts when choosing and designing the power amplifiers and the transformers to keep a relatively flat RF field strength throughout the whole frequency sweep range. Another special consideration is the homogeneity and quantity requirement. As mentioned in the theory part, if we want to use that equation, we need to keep both the B0 and B1 fixed. According to my simulation, as long as the field variation is within 5% and the phase difference between the 2 RF channels is within 5% from the 90 degree, then the calculated relaxation time is going to be within 5% accuracy from the real value. Here's a picture showing the homogeneity and quadrature simulation I did for the region enclosed by our transmit coil. And the colored volume are the volume that fit both requirements. I then designed a sample holder according to those colored volume to make sure that all the detected signal come from the good region. Just a few weeks ago, I managed to experimentally measure the frequency sweep spectra for DPPH at 3 different B0. Those data points are marked in circle markers with arrow bars. I then calculated the relaxation time from the spectral peak shift and used those relaxation times to do a modified block simulation to get the simulated data. They're marked in dashed line. They fit relatively well with the experiment data, and the relaxation time I calculated was around 33 nanoseconds, much shorter compared to the 60 nanosecond measured at higher fields. This fits the prediction that the weaker the field strength, the shorter the relaxation time. We also acquired a frequency sweep spectrum of DPPH at 0B0 without any static field. Interestingly, there is still a spectral peak. Its position is determined by the RF field strength and the relaxation time. I won't dig into too many details here, but since the RF field strength affects the spectral peak position, so potentially we can use that for spatial encoding of spin densities. In other words, maybe in the future, we can do imaging with RF gradient alone and get rid of all the static fields. So, as a novel relaxation time measurement method, I would say it has its own advantages. The biggest one is that we're doing something nobody was able to do before. By using the equation I derived, the shorter the relaxation time, the bigger the peak shift. And with the capability of doing simultaneous transmit and receive using our system, it is very good for measuring short relaxation time at ultra low fields. Theoretically, we can even measure in the nanosecond range. However, it also comes with some challenges. The first one is it's very difficult to design a broadband transmit circuit. For example, if we want to measure something as short as 1 nanosecond, we need to sweep up to 150 megahertz to cover the spectral peak. It's a very broadband frequency sweep system, and it's hard to design. Another challenge is the homogeneity and quantity requirements. Right now, our sample holder is only like 1 centimeter in diameter and 10 centimeter in length. But if we want to do a bigger field of view or a bigger sample holder, it's gonna be more challenging to achieve those requirements. So now I want to show you how our systems evolved through 5 different generations. First generation, unfortunately, there was no signal and we started to think about backup projects. But after a year of hard work, we were able to get the first signal from the second generation. This is the transmit coil. This is the receive coil. And you can see that the transmit and the receive coil are 90 degrees to each other to give us good signal noise ratio. And just a few months later, we upgraded it to the 3rd generation for spectroscopy. Everything you see here was designed by our genius engineer and built by me, including the PCB boards, 3D printed coil bases and coil shells, and the hand-wound Helmholtz coil pair. And this is the 4th generation. We were using it for 1D imaging. We installed our home-built water cooling system to improve the gradient performance. So this is the 5th generation we're currently using for relaxation time measurement. This picture shows the broadband transmit coil. We installed 8 rows on it to improve the field homogeneity. And this is the high signal noise ratio, a differential receive coil. There's a hole in the receive coil where we can insert our transmit coil through it to make sure that they're 90 degrees to each other when assembled. So by using longitudinal detection, we were able to achieve simultaneous transmit and receive with -80 dB isolation. And combined with the fictitious field theory I proposed, we were able to build a pretty unique EPR system. It's home designed, portable, low cost. It operates at ultra low fields and for spins with short relaxation times. Till today, we were able to demonstrate 3 different applications on it: spectroscopy, one-day imaging, and relaxation time measurement. University of Minnesota recently filed a formal patent for us. In it, we further discussed its other commercial and clinical applications, for example, tumor contouring, because we have the capability to detect magnetic nanoparticles in human body. So if they combine specifically with the tumor cells, we can potentially get a better tumor contouring. And also dosimetry, because theoretically, we can detect those fast decay free radicals generated from radiation therapy. And we're also trying to use our longitudinal detection configuration in MRI to achieve simultaneous transmit and receive MRI. So finally, I want to thank all the people from CMR who have helped us with this project, and also thank my advisor, Professor Garwood, and our engineer, Steven Sadas. I would also like to acknowledge the funding resources, NIH U01 and Malcolm B. Hansen Endowed Chair in Radiology. Thank you for your time, and I'm happy to take any questions.
All right, thank you. Questions, Matt? Can I ask you to go on the other mic? Sorry.
What a really beautiful technique. You mostly focused on relaxation. And you did show that spectroscopy of the spions, which was interesting. Have you done any or thought about applicability for doing things like, you know, spectroscopy of, say, Overhauser agents, or like things like Temple nitroxides that have multiple resonances? Because for us at low field, this would be a really interesting way to characterize, you know, like a nice simple EPR spectrometer to characterize things like that.
Yes, spectroscopy is a big application of our system. So this one was done low field sweep spectrum on iron oxide nanoparticles, but we've also done something on the Temple, okay. And we were not able to observe multiple like resonances. Anyway, it could be because we're at different RF transmit frequencies, and we're interested in that. Thank you.
Yeah, thank you.
Hi, I had very nice talk. I have perhaps a more naive question. It looks like the sample space that you designed had no sharp edges. Is that, am I reading that correctly?
Like this one?
Yes.
Okay. Oh yeah, so so the colored volume are the volumes that are good region, but you know, it's very difficult to 3D print a shape like this, like a flower. So we only took the biggest diameter on each surface. So that's why it has a cylinder-like shape, but it's sharpened at the ends.
Okay, thank you very much.
That's a good question.
I was really fascinated by your use of the fictitious field to generate polarization. I was hoping you could maybe quantify that for us a little bit more. So I guess specifically, could you comment on the amount of polarization, how it would like how much of a magnetic field you would have to apply to generate the same amount of polarization that you have here? And also, what are the limits in terms of how much B1 power and how much offset you can actually, like how high your frequency can go? Yeah, just to kind of quantify this entire picture a little bit more, that would be awesome. Thank you.
Sure. Thank you for your question. So I have to admit, if you want to use a fictitious field to generate the polarization, you will get way less compared to the B0 field. So that's why we're mainly use it, like modulate the fictitious field to get the signal we want. And that's why we're using the longitudinal detection, because we need to improve the signal noise ratio to capture that. And I would say if we use like, and also it's limited by the RFL strengths you can use, because typically you cannot exceed several Gauss at RFL strengths. So if you take a look at this plot, this equation, you would tell that I would say the polarization we get is probably 100 times smaller compared to using the same B0. So that's why it's only possible to use RF gradient to do image in the future. We probably need to use some squid or even higher signal noise ratio detector to achieve that. Did I answer your question?
Yes, thank you very much.
Thank you.
All right, please join me in thanking Xuyan again. All right, and the final speaker in the session is Stephen Duviens from Scalar Magnetics. And the title of his talk is No Resolution, No Problem. NMR Spectroscopy at Low Magnetic Fields. But we need the right slides. Oh, I'm on.
Okay, thank you. So I'd like to thank the committee for inviting me to talk today. This work was funded by the NSF through the STTR program, through my company Scalar Magnetics, and working with Matt Rosen at Harvard. So why are we interested in going to lower fields? We keep seeing higher and higher field instruments that give us better resolution and better SNR. However, we're now at the point that some groups can make whole spectrometer electronics at very tiny sizes, basically spectrometers on a chip. But it would be nice if we could also perhaps make a magnetic field low enough that we could fit the magnet on a chip as well. Also, it's common to do in situ measurements for oil field exploration, for example, at low field, but right now they're relegated to relexometry. So it might be interesting to get spectral information in those cases. And thirdly, we're investigating alternative detectors such as NV centers at Diamond, and those happen to work better at low fields. Now, we might get some encouragement from MRI because MRI has been scaled to many different sizes over orders of magnitude of both physical size and magnetic field strength. And in fact, the data I'm going to show today were taken in Matt Rosen's 6.5 millitesla MRI instrument. Now, the reason we can take images of Matt's brain at 6.5 millitesla is because MRI scales nicely. The physics doesn't change over these many orders of magnitude in field strength. Unfortunately, the same cannot be said for NMR. So, for example, if we try to measure the spectrum of ethanol here at field strengths below 100 milliteslas, our spectral information is lost, and the line simply coalesces into a single spectral peak. This isn't just due to a lack of resolution, it's due to an actual change in the physics when the J coupling becomes greater than the frequency shifts. For that reason, if you wanted to work at low field, typically people need to do either relexometry, where they're simply doing T1 or T2 or diffusivity measurements, or do some form of heteronuclear J coupling spectroscopy, such as including a carbon-13 in your system. Unfortunately, this requires using enriched samples many times. Recently, we have come up with another way of doing spectroscopy at low field, which we call now homonuclear J coupling spectroscopy. And we've gotten rid of this need to have a heteronucleus. The way we do it is actually quite simple, but not intuitive. We perform this very simple experiment, doing a 90-degree pulse followed by very weak spin locking, here with nutation frequencies on the order of 0 to 30 hertz. And then we acquire the single line spectrum each time. We perform this experiment over and over at different nutation frequencies. And if we plot the intensity of this line versus nutation frequency, do a little background correction, we typically see from many molecules, one or more dips. So why does this happen? To understand it, we need to understand what our states are under the strong coupling conditions that we see at low field. So if we take a simple 2-spin system and have no coupling, we would just get 2 spectral lines like at high field. But if J coupling becomes stronger than the splitting, we rearrange our states into triplets and a singlet. It turns out then that the spectrum we see consists of a main line, which is simply transitions between triplet states, and possibly some satellites, which are singlet triplet transitions, which are highly suppressed by the symmetry difference between the singlet and triplet states. Now, if we move into a rotating frame, we can make triplet states which are all degenerate and separated from the singlet by a gap J. But we find that something very interesting happens if we do spin locking. The triplet states actually split in proportion to the spin locking strength in a way sort of analogous to the AC Stark effect. And if we spin lock with a nutation frequency equal to J, we get a crossing where a T and a singlet state are at the same energy. Now, this is actually a level anti-crossing as if there is a chemical shift difference. And if we were to sit at this anti-crossing, we get a coherent magnetization transfer from triplet into singlet. If we then take our FID, we get a dip in the intensity because the singlet state is a dark state that we can't detect. On the other hand, if we do the same experiment at other frequencies, we simply get the same magnetization we had before because there was no transfer. In our first slick paper, for example, we performed the experiment on this very isolated spin pair of protons at high field, and we get a dip showing that the J coupling was around 17 Hertz. Now, what happens if we have many more spins instead of just a 2-spin system? Here we have some molecules that all have a methylene group coupled to a methyl group. So we have a 5-spin system. And then we have to draw a much more complex energy diagram. Now we don't have singlets and triplets, we have more complex stress states labeled by their total quantum number and the angular momentum spin quantum number. And we find that at appropriate selection rules, basically delta F and delta M plus or minus 1, we would have level anti-crossings where we get dips. For this particular case, they happen at 3J/2 and 5J/2. And we experimentally show that we get nice dips at those locations. Now, some of these also have protons in the methyl group, for instance, but because it's so far away, there's no coupling and it doesn't contribute. Similarly, for ethanol in a hydrated state, the proton has such a short lifetime due to exchange that it does not contribute. If we had more spins, we get increasingly complicated spectra, but they're different from each other, so we can identify what the different chemicals are. For example, in anhydrous ethanol, we do couple in our hydroxyl proton because there's very little exchange, and so we get a very different spectrum from the hydrated case. We can also do spectroscopy in the presence of the quadrupolar nucleus, which has very little coupling to, or effective coupling anyway, to the protons, so it doesn't cause any problems. The main problems start to occur when we have a lot of protons together, as they sort of form a continuum and degrade our spectrum. We can use the technique to tell apart various isomers, both structural isomers and cis-trans isomers, because the J couplings and the molecular connectivity are very different. So for example, we can easily tell cis and trans dichloropropene apart. Unfortunately, there's some weaknesses to this method with SLIC. First of all, it's very sensitive to B0 shifts. So fortunately, Matt has a very nice lock system on his magnet, keep B0 stable when trucks drive by and doors open. But in the real world, that might be difficult to achieve. Also, B1 inhomogeneity can lead to line broadening, especially of these higher frequency dips. And we need to calibrate the nutation frequency for a series of amplitudes to make sure we get a good calibration curve. So that takes time. To ameliorate some of these problems, we developed an alternative method now based on J-synchronized echoes. And the idea here is that a pulse train has sort of an analogous frequency detection to a spin locking pulse. In fact, we can write an equivalent spin lock nutation frequency, nu n, which now depends on the time delay between the 180-degree pulses. So we can do an analogous experiment to SLIC, now keeping the total length of time equal, let's say a second, and changing the number of 180s that we do in our pulse train, each time also changing tau, so that we are sensitive to different frequencies. Now, instead of using a crossing to achieve polarization transfer, we're actually transferring a triplet-triplet coherence and making it into a singlet-triplet coherence. And we do that by performing our 180-degree pulses at the appropriate time. So the delta nu, the chemical shift differences, mix the triplet a small amount with singlet, but if we didn't do anything, we would just get a little bit of evolution up here at the top of our block sphere. However, if we pulse at appropriate times, we can keep our system on the correct side of the block sphere so that this transition can build up. And if we compare slick versus synchronized echo, for example, for ethyl acetate, we now see that we can get bigger dips. Part of this because the way the physics works, we actually get better transfer. And also because we're less sensitive now to P1 and P0 problems, we get a much higher contrast to noise per scan than we did with slick. Unfortunately, we cannot arbitrarily choose spin lock mutation frequency now because it's a function of the number of pulses, which is a discrete number. So we can't get quite as high of a resolution. To fix that, we further improved our sequence by noting that we have a lot of extra dead time in our pulse sequence where we're not doing anything. So we can actually fill in the gaps by performing echo acquisitions now in between each 180-degree pulse. And we can do a few things with those. So we can use them to average all of these echoes, which helps improve our SNR greatly because now we're taking data over a much longer time. Or we can actually do a form of 2D spectroscopy where we also plot the dynamics as the sequence occurs. So now for ethyl acetate, we were able to get a contrast to noise per scan of around 110. That's around 30 times better than our original slick. And we can also use composite pulses now in our sequence. So the dashed line here is using a composite 180-degree pulse, which gives us a little more improvement by getting rid of effects of inhomogeneity. Alternatively, we can plot each echo versus time, and we can see the dynamics over time of these dips forming. We found some interesting things out about these dynamics. So we can actually perform a similar experiment with slick. Unfortunately, it's slow because we have to do it over and over at different spin lock durations. But if you do that, we find for ethyl acetate that our signal reaches a plateau with a little bit of oscillation due to, which is a reflection of the chemical shift difference. But spin locking longer doesn't really help our SNR. On the other hand, using these synchronized echoes, we should get a much, much deeper dip, which would give us a better signal. Now, surprisingly, we don't see these oscillations. We just see a monotonic decrease. And this could be because we're not considering relaxation of these coherences in our model. Something we need to further investigate. The important point, though, is that we get a much stronger dip. So now on to some applications. First of all, we can do many of the things you would do with normal high field NMR. It's already showed we can identify a lot of chemicals and tell them apart from one another. We can also measure mixtures and do some fitting to figure out how much of each chemical we have. So for example, here we have a mixture of N-methylpyrrolidone and 2-butanone in a 50-50 concentration. And with some fitting, you would get the quantities out with an accuracy of maybe plus or minus 5 or 10%. This was with slick, and we should be able to do much better now with synchronized echo. So those things we can do maybe never as well as high field, but we can now do them at low field. Can we do anything better than at high field? There's two things that possibly we can. One of them is that we are very sensitive now to weak J couplings, which normally would only be detected maybe in high resolution spectrum, but actually unlikely because they would just show up as a broadening in your peaks. So for example, 4 bond couplings on the order of hundreds of millihertz, a tenth of a hertz would just be that much line broadening. On the other hand, here we find that, for example, in 1-propanol, we do a simulation, we see that on the order of a hertz shift causes a couple hertz shift coupling, or not coupling, but shift in our main dip, and also changes in these smaller dips. So by matching with our measured spectra, we can now measure these low field or these very weak couplings. So around 0.15 hertz. And another nice thing is we get the sign for free. Here's some other examples. For example, in dichloropropane, we see a coupling around minus 0.1 hertz. And in methyl isobutyl ketone, we actually do see something about 0. In this case, instead of a shift, we would have gotten this sort of split pattern, which we don't see. A second application is chemical exchange. So I showed you before ethanol at very fast exchange and very slow exchange rates, but we can actually calculate spectra at intermediate exchange rates as well. And we followed some work by Danilo Barsky and others who were doing this at 0 and ultra low field. And we simply assume that at each exchange event, all the coherences involving this exchanging proton are reset to 0. So we can do a Monte Carlo simulation, and we can simulate what all these are at different exchange rates. We see a nice smooth decrease in some of the dips and shifts in other dips as we go from 0 exchange to infinity. We can control the exchange, for example, by adding water or some other alcohol. Now, to make this more scientific than just matching by eye, we decided to train a drone neural network, which Matt's lab has been using for some other work, and to use it to find the exchange rate from a given spectrum. So Matt's student, Nick Hindley, has worked on this. Drone was originally designed to basically to extract data from magnetic fingerprinting information to give parameters like T1 and T2. But here we've commandeered it to take our slick spectra, perform drone, and then get out a exchange rate. And from the training data, we expect we can get a precision of around plus or minus a few hertz over the exchange rates we're interested in. So for example, here we have some measurements with low exchange rates, and we see a nice match that drone got to around 5.7 hertz, and at much higher rates to around 200 hertz. And it does a pretty good job of fitting our real data. So we performed this experiment with a variety of, or basically a range of concentrations for water. And then we looked for some data in the literature to match it with, and we actually had a hard time finding any. Now, the best information we found was from Luz and Maiboom all the way back in 1959, where they said that the exchange rate of ethanol with water should be around 0.8 exchanges per second per molar. And indeed, if we look at low concentrations of water, we get something that matches pretty well. However, surprisingly, higher concentrations, we see that it very much deviates from that line. If we plot on a log scale, we actually see that an exponential fit does much better. Currently, we don't really understand why that is, but it's something we can now pretty easily investigate. And we're currently working on getting some XC data and other independent checks on this to make sure our theory is correct versus, say, the theory of exchange. You can do the same thing on other alcohols. Here, we have ethyl lactate, which has the benefit of having two separate groups that don't really talk to each other. So we can get sort of a reference group on this side and another group which changes as we add water due to exchange. So these dips form as the proton becomes less well bound. So with that, I'd like to conclude. SLIC and synchronized echo can measure unique spectra for many molecules at low field strengths. And now no heteronuclei are required. The only requirement is that the chemicals have a small chemical shift difference somewhere in it. So something like water or acetone are not going to give you any dips. And this method is particularly sensitive to long-range couplings and chemical exchange. So it's a good way to measure those. But we need to now explore more the effects of relaxation, which we haven't really put into our model. So thank you, and I'll take questions.
All right, are there questions?
Great talk. Thanks very much.
Thanks.
I have a question related to the J-synchronized echoes.
Okay.
So,
Yeah.
so as I understand it, I mean, the parameters, the number of echoes in particular depends upon basically the ratio of the homonuclear J coupling and the inequivalence, right?
Right.
So I guess in one extreme, you need a ton of echoes in order to get efficient interconversion.
Right.
On the other extreme, you know, one echo will barely convert it. So
Right.
is there some tuning of the magnetic field that you need to do in order to get kind of an optimal regime where you get good conversion?
Right, and it's the same with SLIC. There's sort of an optimal range of fields. So 6.5 milliteslas actually is very good. Maybe 10 milliteslas would be a little better for most molecules. Now, if you go too high, all these exchanges or the magnetization transfer happens too fast. And if you go too low, it takes too long compared to relaxation. So there's sort of a good range between 1 and 100 milliteslas generally. We also have some data from 0.5 Tesla on aromatics, because in those cases, the chemical shift differences are very small. So we have to go to a higher field to make it work.
Thanks.
Hi, two questions. Very nice presentation. The first is that looking at these multiple echo sequences suggests there might be something interesting with something like an Uhrig dynamic decoupling sequence with unequal spacings between them. Have you thought about that? And there's a deconvolution problem, but there's also some relaxation compensation you would be doing.
Yeah, I've thought a little bit about it, but I haven't really simulated it yet. Yeah, it could be a way to get more information within each sequence, for example. You know, sort of like the idea of Hadamard sequences where there's some other eigenbasis that you're looking at that might be more efficient. So
And,
yeah, I
and my
agree.
second question, and I've seen you present data like this before. I've never quite figured out the brown lines on your
Oh,
figures.
sorry. Okay. So
Yeah.
for SLIC, the SLIC ones are kind of noisy, so we've always been fitting with just a series of dips, for example, Lorentzians, to show where those dips are. Now with synchronized echo, this is just the data directly drawn as a line because we have much better SNR. So
Okay.
that's
All right, thank you.
I guess my questions are a little bit related to Warren's. If I understand, I haven't seen this sync echo before. It's very beautiful. You need to know the chemical shift difference to have an efficient dip. Is the chemical shift information somewhere in the setting up of this spectrum?
So the chemical shift information is inside the simulation. So we put in the full information of J coupling and chemical shifts to get out the simulated.
But from there you get the timing of the echo. I mean, you
well,
have
so
this
we
rotation in triplet singlet space, and you have to hit the pi pulse at the right frequency, let's say, at the right phase. So that means the chemical shift evolution is
right.
somewhere there.
But the nice thing is, in doing spectroscopy, this isn't designed to actually, do the transfer specifically in a case. It's designed to scan what those are. So, we could take a chemical where we don't know that, and when we do the series of experiments, we either get dips or we don't, right? We don't need to tune it beforehand to make it work. We just need to be in a general field strength where it would work.
My second question would be, if you were to scan these parameters,
Yeah.
could you somehow get a 2D correlation between these protons and take these broad lines and resolve, say, connected transitions should be in this case, right?
Right. So, I mean, in an ideal world where there's no relaxation, we would get all of this dynamics, and then we'd be able to tell exactly what the chemical shift and J couplings are. But as you can see, they're kind of washed out because of relaxation on the same timescales we're measuring. So we're mostly focused on the J part.
Okay, one last question.
I'm sorry, but I have to ask, sensitivity. So I assume most of the stuff that you've shown have been pure compounds?
Yes, so these are all liquids because we get a lot of nice signal that way.
And have you tried some sort of dissolved, like, I just want a broad range, like millimolar or something?
We've done like 10% concentrations of ethanol, for example, in D2O. So I mean, we can get lower, and we could calculate it from these, contrast to noises I show. But yeah, we're definitely hit in sensitivity because we're at 6.5 milliteslas. Now, the nice thing about 6.5 milliteslas is that Omri works well at those fields. So, we're thinking of things like that to maybe boost us 100-fold or so in the future.
Awesome, thank you.
All right, please join me in thanking Stephen and all the speakers from this session again. All right, that is the end of the session. There's coffee break outside, and we're getting started again at 10:45.